So in today's lecture, I will be doing the solutions of some exact solutions of some viscous flow problems. Exact solutions. So to start with, I will do the solution of the viscous flow between two parallel plates. So these are two parallel plates. This is the center line. Parallel plates. So I will set the x-axis along the center line and y-axis. So, and I denote H as the gap between the plates so that this distance from the axis is x by 2, and there is a fluid flowing, viscous fluid flowing between these flat plates, and we are seeing the flow as laminar, then incompressible. So these are the assumptions. And we assume that it's actually it's a flow between two plane plates. That means it is extending in the z direction to a larger distance, so that we can assume the derivatives in the z direction is equal to 0, and also the velocity component fluid motion along that direction is also equal to 0. So that way we are assuming two-dimensional and in the xy plane, two-dimensional in the xy plane. And we'll add to some more. I will make some more addition to these assumptions later. So for the two-dimensional flow, in the Cartesian coordinate system, we have the expanded form of Navier-Stokes equations. U by dou x plus v dou u by dou y is equal to minus 1 by dou p by dou x plus u into dou squared u by dou x squared plus dou squared u by dou y squared. And also we have other equation continuity dou u by dou x plus dou v by dou y equal to 0. And this is for the x momentum. And there can be a similar equation for y momentum also, but we may not need that for the exact solution, this particular exact solution. Okay. So I will not write it, time being I will not write. And another important assumption we do for this, for making an exact solution for the flow between parallel plates is it is developed. The flow is developed. So the meaning of developed flow means, so for in a channel like this, the fluid will be entering with a uniform velocity. Uniform velocity. So maybe that is the same length, same magnitude velocity. So as soon as it enters the channel, on the wall there is a condition in viscous flow. So on the wall, the fluid particle will be stopped, or fluid will not. the fluid particle sitting adjacent to the wall will not be slipping. So, or it is called a no slip. No slip. That is one of the boundary conditions or one of the assumptions we do in the case of viscous flow. The fluid particles on adjacent to the wall will not be slipping or no slip. That means both the velocity components u is equal to 0, v is equal to 0. So immediately, as soon as this fluid, which is having the average velocity, approaches the wall, and it is stopped in that the direction of motion, so naturally fluid particle will be moving up. So there will be a certain amount of v velocity set in, but there is a reduction of u, but there is an increase of v from the inlet condition is u is equal to some capital U average velocity and v is equal to 0 with the 0 v at the inlet. There will be a development of v velocity immediately inside the channel. So like that, so the resultant velocity will be something like this. So there is a movement of fluid particles towards the central region, and so like that, as it proceeds through the gap between these plates, at certain point, the velocity would become like this. So so velocity will be peaking at the center line and will be reduced and become 0 for the no slip condition on the wall surface. So, and later on, once this kind of a velocity distribution is set in, the velocity distribution remains same in the downstream of that particular section. The velocity distribution remains the same. So we'll have the same distribution. Yeah. So that means if you are talking about this u velocity, the u velocity does not change as x changes. So or dou u by dou x is equal to 0. So this type of a condition is called wherein the velocity does not change along the direction of motion of the fluid is called developed flow. So developed flow, mathematically we can write dou u by dou x is equal to 0. So now we look at this particular equation. So this particular equation. So that is the continuity equation. So in this, for developed condition, this dou u by dou x, so this is equal to 0. Then this is dou v by dou y. So for to satisfy continuity, dou v by dou y has to be equal to 0. And already we talked like dou u by dou x is equal to 0 and dou v by dou x is also equal to 0 if at all there. So dou v by dou y equal to 0, dou v by dou x is equal to 0, that means v is a constant. So that implies v is equal to constant. Then only dou v by dou y is equal to 0 and dou v by dou x is equal to 0 can be satisfied. And also we know that v is equal to 0 right on the wall, v is equal to 0. So v is equal to 0 also, but v is equal to constant also. So those two conditions can be satisfied only if we say that v is equal to 0. So that way, the developed flow condition along with the continuity yields the condition that v is equal to 0. So now we look at the x momentum equation, and this term becomes equal to 0 because dou u by dou x is equal to 0, developed. And subsequent to that, consequent to that, we are having v equal to 0. So this term is equal to 0. And as far as this term is concerned, dou u by dou x is equal to 0 everywhere. So dou squared u by dou x squared is also equal to 0. So so we cannot talk anything about this and anything about this, we don't know. So the x momentum equation, therefore it becomes minus 1 by dou p by dou x plus mu into dou square du by dou y square equal to 0. We get the x momentum equation simplified to this form. And also, the dou u by dou x is equal to 0. That means u is a function of y only. So dou u by dou y is equal to du by dy. It can be written as the total derivative. And when this kind of identical velocity distributions are there, the pressure dp by dx, dou p by dou x, that is pressure is varying, right? Pressure is varying, and that variation also will be linear because the velocity is identical. So dp by dx will be essentially dp by dx. Suppose at the inlet, this is the inlet and this is the exit. So inlet point, if I mark it as 1, mark it as 2. So there is a pressure P1, there's a pressure P2 will be acting like this. So this dp by dx is, suppose this is L, dp by dx is P2 minus P1 by L. P2 minus P1. Over the entire channel. Also, this also will be equal to the dp by dx at any point. So the dp by dx will be, so dou p by dou x will be dp by dx, and that will be same as P2 minus P1 by L. So that is the externally applied pressure gradient. So we can rewrite this equation, this resulting equation as 1 by rho dp by dx plus mu into d square du by dy square is equal to 0. So this is the kind of equation we get, where this is something forms an input for the velocity to set inside the channel. So naturally, if suppose if P2 is more than P1, P2 is more than P1, P2 is more than, suppose P2 is more than P1, then this is a positive pressure gradient, positive pressure gradient. So that means this P2 is more than P1, then the fluid particle will be pushed like this. So the velocity would be the negative x direction. If this is the x direction, velocity will be in the negative x direction. If P2 is equal to P1, P2 is equal to P1, essentially there won't be any flow that we will see. P2 is equal to P1, that means dp by dx is equal to 0, there won't be any velocity. If P1 is more than P2, P1 is more than P2, that means then dp by dx is less than 0. Less than 0. So in that case, the P1 is more, so fluid particles will be starting to move in the x direction, in the positive x direction. So what is the kind of developed velocity distribution that is governed by this particular equation? So this is an ordinary differential equation with dp by dx is constant, right, given as an input to the calculation. So this we have to do the double integration. So first integration will give, okay, we will write mu into d square du by dy square is equal to 1 by rho dp by dx, and integrating once we get du by dy equal to 1 by rho dp by dx y plus some constant c1. So where c1 is a constant. Now let us get into some of the boundary conditions. So if we talk about the boundary conditions, so this is a center line, and where the du by the velocity will be peaking at the center line. And by that condition, so our velocity distribution is symmetrical. On the top of the center line and bottom of the center line, velocity distribution will be symmetrical. There is no way the velocity distribution can be asymmetrical. That means the tangent like that, tangent that is the du by dy is equal to 0 in the y direction, du by dy tangent in the y direction if we take, that is du by dy is equal to 0 at y is equal to 0. That is, this point is y is equal to 0. Y is equal to 0 is this point where du by dy is equal to 0 here also. So du by dy is equal to 0 at y is equal to 0. Apply that condition. So at y is equal to 0, I am going to have this one 0 when dp by dx into 0, y is equal to 0 plus c1. So what is that? Implies that c1 is equal to 0. So thereby we get u into du by dy is equal to 1 by rho dp by dx into y. So integrate once again, integration, integrate mu into u is equal to 1 by rho dp by dx y squared by 2 plus some c2, another constant. Okay, so u into u. So u into u, or u is equal to 1 by rho nu dp by dx y squared by 2 plus c2 by nu. Okay. So nu is a constant, that itself we can treat it as another constant. So C2 is a constant, nu is a constant. Okay, let it be like this. So u is equal to 1 by rho nu can be written as mu dp by dx y squared by 2 plus c2 by nu, and this is a function of y we get. Now another condition is on the solid wall here u is equal to 0. That is where y is equal to s by 2. At y is equal to s by 2, u is equal to 0. So at y is equal to s by 2, u is equal to 0. So that substitute here 1 by mu dp by dx. And this is y squared is h squared by, that's a 2 is there, into 2 squared is there 4 plus c2 by nu. For that gives c2 is equal to, this there's an 8 is there, 1 by nu dp by dx h squared by 8 nu, and with the negative sign, and I have a nu over here, and then I will be substituting it back. U of y becomes 1 by nu dp by dx y squared by 2 plus 1 by nu into c2. C2 is minus 1 by 8 nu dp by dx h squared nu, and this nu cancels. So 1 by nu is here, dp by dx is something constant, and I will have a multiplication of 4 and 4. This 4 into 2 is 8 will come. So I have an 8 here. So remaining there's a 4 y squared over here, minus 1 by 8 nu is taken outside, dpj is taken outside, minus h squared. This is a kind of velocity distribution. So it is a second degree velocity distribution. That means it is parabolic like this. So it's parabolic like this. So we have got the equation for this equation of this parabola. That is some 4y squared minus x squared. 4y squared, 4y squared minus x squared into there is some constant k. The remaining things are some constant. So dp by dx is a constant, viscosity fluid is constant, H is constant. So this is the kind of velocity distribution, the parabolic velocity distribution for the flow between parallel planes develop the flow. And if you further, if you want to do some calculations, the one important thing you can calculate is the wall shear stress. What is the wall shear stress? So what is wall shear stress? Is the toe, which is the toe wall equal to mu into du by dy at the wall. At wall here it is y is equal to x by 2 because wall here is at y is equal to x by 2 and this is the point. So compute that. Already we are having du by dy, du by dy is this particular equation. So this particular equation, let's take this equation. So the so I want the toe wall equal to mu into. So you multiply with the rho here. So multiply with the rho here. This rho is okay. And at y is equal to s by 2. So uh, no, we will substitute. No, we will not do this. We will substitute the velocity so that we will get in terms of velocity and height. So, what shear stress is rho u into du by dy. So I am having u expression for u like this. So rho into u into dou u by dou y. For that u is like this. So I have 1 by 8 mu dp by dx. And the derivative of this is 8y minus 0. And this y I have substitute at y is equal to s by 2. And this y has to be substituted is equal to h by 2. So then it becomes, so this 8 and 8 cancels. It becomes toe wall becomes rho nu by mu is rho nu by mu is okay. So essentially it becomes the same thing. Okay, rho nu by this becomes so dp by dx into s by 2. It becomes dp by dx so that the previous dp by dx into s by 2. So this is a wall shear stress. So wall shear stress or velocity, this velocity depends upon the input dp by dx. Input dp by dx. So velocity is dp by dx is positive. dp by dx is positive. At any point, okay, this is there is a 4y squared minus x squared. By 8. Okay, maximum value of y is s by 2. S by 2. Maximum value of y is s by 2. So 4 into h squared by 4, that is x squared. So the maximum value of this will be 0. Maximum value of this will be 0 because maximum value of y is s by 2. Maximum value of v is 0. So dp by dx is positive, then you can have only negative velocity. That is, flow will be taking place in the negative x direction. If dp by dx is negative, then we'll have the positive velocity fluid flowing like this. So next another thing which we can calculate is the total flow rate. Total flow rate through the channel. So what is the total flow rate through the channel again? and draw the channel, and we are having the velocity distribution like this. So something like this. So again, there's something like this, something like this. So this is h by two. This is h by two. So these are two symmetrical regions. So the flow rate through the top and flow rate to the bottom are same. So this is y is equal to 0 and this is y is equal to h by 2. We take a small strip at some y of size dy, and there is a u of y, and the discharge to the strip is u of y into dy, and let us assume unit height. So the total area, this is a discharge through the small strip, and it is integrated from 0 to h by 2, and this is for the half, then twice of this is the total flow. So we have twice integral 0 to h by 2, u of y expression, we got the u of y expression. U of y expression is basically u of y expression is this particular 1 by 8 u, 1 by 8 u dt by dx, the 4y squared minus x squared into dy. So these things are constant. So 1 by 8 to 1 by 4 mu dt by dx, integral 0 to h. So that can be 4y cube by 3 minus h squared y from 0 to h by 2. H cube by, sorry, h squared. Sorry, h squared y. This is h squared y. H squared into y. 4y cube by 3. So 1 by 4 mu dt by dx into 4 into 4 by 3 into h by 2 the whole cube, h cube by 8 minus h squared into h by 2, that is h cube by 2, and this 4 cancels and 4 you know, this 4 cancel and this 4 comes here as 8. 8. So I will have 3. It goes 3 into 8, 1 by mu dt by dx into 24 h cube by h cube minus 3 h cube. H cube minus 3 h cube is minus 2 h cube by 24, that will work out as 1 by mu minus dt by dx, minus dt by dx h cube by 4. So this is the equation for discharge. And when dp by dx is negative, then only discharge is positive. Discharge means going towards right. So when dp by dx is positive, you will have the flow rate coming from right to left. Right to left. So that way, the sign of the dp by dx influence the kind of the flow rate. So in one direction, so fluid is flowing from this into that end, depending upon the sign of, because we need dp by dx to be negative for the flow to take place in the positive direction. So that is the meaning of negative dp by dx. So this is about the flow between parallel plates. One more exact solution will work out in this lecture, that is force flow. The Couette law is a slight modification of the flow between parallel plates. We have one plate like this. So we have got certain fluid filled in this particular in the, above the plate, and there could be top boundary. There's a top boundary also. There's a top boundary. We assume that the top boundary is moving with some velocity v, capital V. And this is a stationary one, and top wall is moving. And this is a plane flow. It's called a plane flow also. And here also the assumptions are the same assumptions we use, so that the simplification done up to the assumptions and simplification done up to writing this equation, up to writing this particular equation is applicable for this flow also, this shear flow also. So the same assumptions, the same assumptions the same assumptions we use. Same assumptions we use and write minus 1 by rho, not dou p by rho s, we write it as dp by dx plus mu into d squared du by dy squared is equal to 0. And the only thing is that the boundary conditions vary. So boundary conditions vary here. We take x-axis like this so that the y distance is measured from the bottom wall. Y distance is measured from the bottom wall. So let the height of the height between the top wall and the bottom wall is h. And here this is stationary, so u is equal to c over here, and u is equal to capital U over y is equal to h. These are the boundary conditions. So, and this problem also, the u causes the velocity of the droplet causes some fluid motion inside that. Along with that, this pressure gradient term also causes the fluid to be displaced from one end to another end. And that again depends upon the value of the pressure gradient. So you can have the P1 and P2, P1 and P2, P1 greater than P2. In that case, the dP by dx is P2 minus P1 by L, total length. L is total length, and this becomes the P2 is more than P1. This becomes less than 0. So that is P1 is more than P2. So it is naturally the P1 is aiding the flow. So it is this condition is this kind of a pressure gradient is called a favourable pressure gradient. Favourable pressure gradient. Negative pressure gradient is favourable pressure gradient. You can have a condition when dP by dx is equal to 0. That is called zero pressure gradient. You can have a dP by dx greater than 0. So in that case, the P2 is more. So the pressure will be acting against the motion of the wall, and the motion of the wall causes the fluid to move like this, whereas the pressure causes the fluid to push in the opposite direction. So this condition is called an adverse pressure gradient. Adverse pressure gradient. So this will be forming an input. dP by dx will be forming an input along with the wall motion of velocity with the velocity capital U. So the same kind of integration we do, and here you have d squared u by dy squared is equal to 1 by rho dp by dx, and I will take this mu to here, so that this is 1 by mu dt by dx, and integration of this is du by dy is equal to 1 by mu dt by dx y plus some constant c1, and again once again integrating, you get u of y is equal to 1 by mu dt by dx y squared by 2 plus c1 y plus c2. So we have got two constants, and it can be evaluated by using these two conditions, this condition and this condition. And we have u of y is equal to 0 is equal to 0. That gives implies 0 is equal to 1 by mu. This y is equal to 0, or dt by dx into y squared becomes 0 plus c1 into 0 plus c2. So this implies c2 is equal to 0. So we have this getting into 0. So now again u of y is equal to, we have one more constant, that is 1 by mu dt by dx y squared by 2 plus c1y, and y sorry u of y is equal to h, y is equal to h, that is this y is equal to h, is equal to capital E is equal to 1 by mu dt by dx. This is h squared, y is h squared by 2 plus c1 h. So what is then c1? Or what is then c1 is equal to capital U by h plus 1 by mu dt by dx into h by 2. 1h cancels. And in fact, I want c1y. So c1y can be plus. So totally, u of y can be written as capital U y by h plus 1 by mu dt by dx h by 2y plus 1 by mu dt by dx y squared by. Is there any sign problem in this? There is no sign problem. So you get the velocity distribution u of y is equal to like this. So u of y is equal to uy by x. Okay, c1y c1y. The c1h, actually u is there, this comes to here, and then this has to be negative. This has to be negative. So y is by 2, so this will be negative. This will be negative. So I will have this minus 1 by mu dt by dx. There is 1y by 2 can be taken outside. So 1 by mu is taken, dt by dx is y by 2 is taken outside, dx minus 1 by mu is taken outside, dy by dx is taken, y squared by 2 becomes 1y by 2 is taken outside, so it becomes 1. So we can see whether the boundary conditions are satisfied or not. U is at y equal to 0. We have this one 0. We have this one and 0. Y is equal to 0. So here, okay, y is equal to 0. Here there is a 0 is there. So that makes y equal to 0, velocity is equal to 0, and u is equal to h. This will get this one, then y is equal to h minus h becomes equal to 0. The boundary conditions are satisfied. So this is the velocity distribution. This is the velocity distribution. So okay, in that case, if dp by dx is equal to 0, dp by dx is equal to 0. If dp by dx is equal to 0, u of y is equal to u by h y by h u into y by h. It becomes y by h, and I can write as y by h into capital V. So this is a linear radiation. So the zero pressure gradient for the flow, zero pressure gradient gives rise to a velocity like this. So actually there is some problem with this. Uh, uh, Okay, so this kind of velocity distribution, this is the capital, this is capital, and this equation is capital U C, sorry, U is equal to capital U into Y by this X, like that. And there can be velocity distribution different. Okay, the pressure gradient, depending upon the pressure gradient, the velocity distribution could vary. So I'll take this there. So, so this is the equation. This is the equation. So we can have a velocity distribution. Okay, let us find what is du by dy. What is du by dy? Du by dy is also possible. It is possible to write du by dy also. Du by dy. Du by dy. We write du directly. Du by dy is equal to, from this, du by dy is equal to u by x minus 1 by rho dt by dx mu yx. Yx differential is x minus y squared, y into y squared 2y. So, okay, what is the pressure gradient? What is the dp by dx for which this is equal to 0? This is equal to 0. This is possible. Okay, what is the dp by dx for which this is equal to 0? So, du by dy is equal. Okay, du by dy at some point, let us take du by dy at y is equal to 0. Suppose du by dy is, okay, du by dy at what? So I want to see what is the du by dy at what, so that I can find the wall shear stress. So what is du by dy at the wall? That is at y is equal to 0. So u by x minus 1 by 2 dt by dx dh, and this is equal to 0, not this one. I'll take what is a dp by dx for which du by dx on the wall becomes equal to 0. So what is that dp by dx is? Dp by dx mu by h, this 2 mu comes here, h comes here. So if you substitute dp by dx is equal, if you take dp by dx is equal to this kind of value, then du by dy on the wall will be equal to 0. Velocity gradient on the wall will become equal to 0. That means we will have a profile something like this. Suppose I draw the velocity variation with respect to y. The velocity will be, and this line will be tangent. So velocity will be like this. So velocity will be something like this. So this kind of velocity distribution we will get. And this is when dp by dx is equal to 2 mu u by if there's an h is there, this h in the h you can write as h squared. I can write as h squared. So divided by h squared. This squared we get this kind of velocity distribution. So if dp by dx is larger than 2u mu by h squared, so then what happens is that the pressure gradient dp, here the pressure is becoming more. So then what happens? So now this flow has become, so the flow was something like this. There was a flow like this that has become almost zero velocity here. So further increase of pressure gradient will cause the velocity distribution to become like this. So will be starting from no slip. It will be starting from like this. So it will be like this. So here it will be positive because this positive because the wall is moving in this direction. It will be positive. So this will be positive. So this will be like this. Whereas you will have a reverse flow in the bottom region because of the pressure gradient. This is for dp by dx. It is adverse pressure gradient greater than u mu u by h squared. So this is called an adverse pressure gradient. And this okay, for negative pressure gradient, this is for zero pressure gradient. This is for dp by dx is equal to 0. So for negative pressure gradients, we will have the velocity variation in the workflow like this. So, velocity should be like this. So this is dp by dx less than 0. That is favorable. The 0 pressure gradient. This is adverse, and the du adverse with this condition is for du by dy at the wall equal to 0. So this one I shared with you. So we can integrate this and write the discharge also because velocity is there. You can do the integration and find out the discharge also. So that I leave it as an exercise.